The biggest shift here is that AI is getting better at deciding which signals to trust, which paths to explore, and which weak labels deserve training on. That matters because today's bottleneck is less raw model size and more whether the system can reliably self-improve without getting trapped by its own guesses. Across these papers, you can see a common trend. Stronger models are being built by turning inference, evaluation, and data selection into structured decision processes. And the results are surprisingly concrete. Let's explore the first paper, Self-Improving Language Models with Bidirectional Evolutionary Search. Self-Improving Language Models with Bidirectional Evolutionary Search from Harvard University and MIT introduces BES, a search framework for self-improvement and test-time reasoning that targets two failure modes of best-event sampling and tree search, sparse verification and candidate generation trapped inside the model's own probability mass. BES adds 4 evolution operators: combination, deletion, translocation, and crossover to recombine partial trajectories, while a backward goal tree recursively decomposes the task into verifiable sub-goals and supplies dense intermediate scores. The paper proves that expansion-only rollouts remain confined to a narrow entropy shell, whereas evolution can escape it, and shows that backward sub-goal signals reduce the candidate requirement from a multiplicative terminal hitting problem to a much cheaper local evidence collection problem. In experiments, BES improves knights and knaves post-training on Gemma 3.1b it, where GRPO and MaxRL show little to no progress, and on MuCK it raises accuracy from 4% to 7% on Llama 3.2.3b instruct, and from 6.6% to 10.4% on Llama 3.1.8b instruct, while also increasing finish ratio to 0.97 and 0.94. At inference, using GPT-5 on open optimization problems, BES outperforms open source frameworks like OpenEvolve, GPA, and Shinka-Evolve on circle packing and Heilbronn, reaching 2.623 on circle packing, square, 2.349 on circle packing, rect, and 0.026 on Heilbronn, convex, with lower variance and modest extra API cost. Let's explore the second paper, Skill RM, Unifying Heterogeneous Evaluation Criteria via Agent Skill. Skill RM, developed by the Qwen Large Model Application Team at Alibaba, reframes reward modeling as an executable agent skill rather than a static scalar judge. The framework packages a reward evaluation skill with a frozen resource bank of rubrics, references, checklists, verifiers, and aggregation rules, then lets a Qwen 3.5 judge dynamically retrieve and execute only the evidence relevant to each input. On Reward Bench 2, RM Bench, and Judge Bench, the match Qwen 3.5.27b baseline averages 83.9, while Skill RM raises that to 86.2. And Skill RM with sample-specific resources reaches 89.1. The stronger Qwen 3.5.122b A10b backbone reaches 86 with sample-specific resources. The mechanism study is important. Directly appending resources drops the average to 81, showing the gain comes from skill-mediated orchestration rather than extra context. In best-of-1 zero selection on JETS pools, Skill RM is nearly saturated on GSM-8K at 97.8, while showing clear gains on IF-Evil and Human-Evil Plus. For instruction-following reward use, Skill RM achieves the highest IF reward bench Kendall correlation at 0.524 and improves downstream GRPO training to 45.9 average on IF-Evil, IF-Bench, and Advanced IF, outperforming VERF at 44.7. Overall, the paper's novelty is the explicit, evidence-bearing reward trace that unifies heterogeneous evaluation criteria into a reproducible reward computation pipeline. Let's explore the third paper, Trust Functions Near Lossless Weak to Strong Generalization by Learning When to Trust the Weak Teacher. This Johns Hopkins University paper introduces neural trust functions, a data selection method for weak to strong generalization that scores each weak label using the weak teacher's internal activations rather than output confidence. Trained on a labeled source set and deployed zero-shot under in-domain distribution shift, the trust function filters weak supervision before training a stronger student. Across world knowledge, quantitative reasoning, and strategy games, the method achieves near lossless recovery, relative to ground truth training, and sometimes surpasses it. In world knowledge, the Quen 306 B teacher yields 61.6% to 87.1% student accuracy and matches or beats gold label training in 5 of 8 settings. In quantitative reasoning, it reaches 22 on Quen 3, 4B, and 27.9 on Quen 3, 8B, close to or above ground truth. In chess, it reaches 44.1 on Quen 314, B versus 39.9 for ground truth. The trust model itself is well calibrated, with AUC up to 0.96 and purity up to 0.98, and chaining the procedure across generations, compounds, gains, culminating in 48.2 on Quen 3, 14B, ahead of the 40 ground truth baseline. Mechanistically, the selected data are easier, more label correct, and induce more coherent low-rank gradients, while some apparent false positives are actually stronger alternatives than the dataset labels. A risk-controlled Hofting calibration rule further turns trust scores into a practical thresholding mechanism, retaining 16.1% of the deployment pool at a target noise rate of 0.1. That's a wrap on today's AI paper highlights. Thanks for watching.